this video will cover the second half of Unit 2 when we discuss chemical bonding and molecular shape. So the first thing we'll do is just review a couple of things, and then we'll do some practice problems. So when we're looking at shape, you will have the card on your test. But we know that shapes can be determined based on the number of lone pairs. So we can just kind of look and see, what does our shape look like? Do we have lone electrons like these do? Or do we just have bonded pairs like the ones on the top? We also want to talk about polarity. So if it's polar or nonpolar. So we mean our polar bonds, okay, they're sharing electrons unevenly. So somebody is hogging these electrons, and it's the one that's going to be most electronegative. Okay, that's the one that's going to be hogging the electrons. Over here we have a nonpolar bond because they're equally sharing those electrons. So we're not really concerned with ionic. Mainly, if you can just remember that less than 0.4 is nonpolar, and then here greater than 0.4 is polar, then that kind of makes it easier. You don't really have to worry about this 0.7. And again, we know that polar is sharing them unequally. Somebody is hogging them, whereas nonpolar, it's an equal share. So here we have some examples. We can see chlorine, it's bonded together. When I look at their electronegativities, I think it's 3.5 and then minus 3.5. They're both 3.5, so the total is 0, which is less than 0.4. So that means nonpolar. When I look at something like hydrogen and chlorine is 3.5 and hydrogen is 2.1. So this is a 1.4 difference if I subtract those, which puts me well into the polar, right, greater than 0.4. So all you have to do is look at the periodic table. On the back, we have the list of the electronegativities, and then you're just going to subtract the two that you have and look and see if it's greater than 0.4 or smaller than 0.4. Based on whether or not we have a polar molecule, we have different types of intermolecular forces. So if you have a polar molecule, we know it's going to be dipole-dipole. Okay, so it has it in the name, think polar, pole, dipole-dipole. If it isn't polar, then it only has London dispersion forces, okay, or LDFs. If we ever have hydrogen that's bonded to an F, hydrogen bonded to an O, or hydrogen bonded to an N, so you can think of it like FON, okay, then we know we have hydrogen bonding. This always occurs in a polar molecule. So if you ever have hydrogen bonding, that means you also have dipole-dipole because it's polar. And then everything has London dispersion forces. The trick is remembering that if you have something that's nonpolar, it can't have dipole-dipole or hydrogen, so it's only London dispersion forces. So let's look at some examples. So when we draw our Lewis structures, the first thing we want to do is count our number of electrons. So sulfur has 6 valence electrons, and then hydrogen has 1, but there's 2 hydrogens, so a total of 2. Okay, so that means that we have 8 valence electrons. I know that sulfur is going to go in the middle because it's by itself, and then I know that hydrogen is going to be bonded to it, so I put hydrogen on each side. Remember, hydrogen can only have one line. It can't have dots, it can't have anything else, just one line. So if I have 8 valence electrons, I know that in each line is 2, so I have a total of 4 drawn right now. So that means I have to draw 4 more dots to get up to 8. So there's my 4 more dots, okay? So now we can look at our shape. So I'm going to scroll So I have 2 bonded pairs and 2 dots on the top. So that matches this one right here. So then we're going to say this is bent. Okay. And if you wanted to, you could redraw it a little bit so it kind of looks a little bit more like the picture, but it doesn't matter that much unless you can, as long as you can kind of remember that that's what it really looks like. So now we can look and see about our polarity. So to do our polarity, remember we're going to look at our electronegativities. And I know hydrogen is 2.1. I can't remember off the top of my head what sulfur is, but I know that their total is greater than 0.4. So, and sulfur has a higher electronegativity. So that means sulfur is hogging my electrons. So I'm going to draw my arrows pointing towards sulfur. And sulfur is going to get a partial negative charge, where my hydrogens get partial positive because my electrons are hanging out closer to sulfur because they're hogging it. So now if I wanted to think about my polarity of my molecule, I have a positive end and a negative end. So I have 2 different poles. So this would be polar. Okay. And then if I wanted to think about my IMFs, I know that a polar, I'll do it in another color, a polar molecule has dipole-dipole and LDF, right? Because everything has LDF. And then I need to look, does it have hydrogen bonding? Is it H bonded with F, O, or N? No, so it's just these 2. Okay. So let's look at chlorine. So chlorine, I know that each chlorine has 7 valence electrons, so that means it's a total of 14. So when I draw my chlorine, I start off by just connecting them with a line because everything has to connect with a line. And now I can just keep drawing my dots until I get up to 14 total. So I know I have 2 right now in the line, so I only need 12 more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's perfect. Everybody has their 8. So 1, 2, 2, 4, 6, 8, 2, 4, 6, 8. So now I'm done drawing. Okay, because remember we want to make sure you can only have this many dots or this many electrons. So some will be in a line, and then everybody wants 8 around them. Okay, so if we think about, one way to think about it is like a circle. So if I was to draw a circle there, right, that means it has 2, 4, 6, 8. And if I was to draw a circle there, it means it has 2, 4, 6, 8. So everybody has their 8. So now let's look at our polarity. So chlorine, both of these are 3.5. So when I subtract, I get 0, which is less than 0.4. So this is non-polar. So I don't have to draw any kind of partial charges because nobody's hogging electrons. Okay. And then when I think about my shape, it's just in a straight line. So when I come back up here and look, here it is. It's just in a straight line. So this would be linear. And then we know that for, we'll write nonpolar. And then we know that for nonpolars, there's only LDF for your IMFs. Okay. All right, SO3. So I know oxygen can have 6 valence electrons. Nope, it's not 24 yet. That's only 18. And then sulfur also has 6. So the total is 24. So when I draw this, I know that sulfur has to be in the middle and oxygens are going to be around the outside. So I just connect them with the lines because everything has to be connected with lines. And then now I can start drawing my electrons. So I know I already have 6 because I have 3 lines and each line has 2. Now I can start drawing till I get to 24. So I'm going to start with 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I have all 24 drawn, but I have a problem. Sulfur only has 6 electrons around it, and it wants 8. I can't draw any more dots, so sulfur is going to have to ask oxygen to share. So what we're going to do is just ask one of these to take these electrons and move them into the line. Okay, so we're going to move them right here and erase them from right there. Okay, so now oxygen still has 8 because there's 2 in each line, so that's 4, 5, 6, 7, 8. And then now sulfur also has 8. So if I was to look at the shape, we'll scroll back up. Notice we don't have any lone pairs around the center. We only have 3 things. Try not to scroll too fast. So that looks like this right here. So we'll say trigonal planar. So close your eyes if the scrolling is making you dizzy. Trigonal planar. Okay, and then we can look at electronegativities. So in this case, we will subtract, let's see, we'll do green. So if I look at the electronegativities for sulfur and oxygen, again, I can't remember exactly what they are. I think it's 3 and 3.5. But when you subtract them, you should get something that's greater than 0.4. And oxygen has the highest electronegativity. It's a little bit higher than sulfur. So we're going to say oxygen is hogging the electrons. So oxygen gets a partial negative, and then sulfur in the middle would get the partial positive. So when we try to figure out the polarity of our molecule, we have to look, do we have a positive end and a negative end? And the answer is no, we have a negative end, and a negative end. So this molecule is non-polar because there's no opposite ends. And a non-polar molecule only has LDF. Okay, so the reason it's non-polar is even though it has a polar bond, you have to think about the shape. And because it's a trigonal planar, everything is spread out evenly. The negatives are all around the outside. So there's no opposite sides. Okay, last one, nitrogen and hydrogen. So hydrogen has 1 electron, and then nitrogen has 5. So that's a total of 8. So I have 3 hydrogens. So remember, we always just put the thing by itself in the middle. And remember, hydrogen can only have a line, so it's connected to a line. So that means my last little lone pairs have to go around nitrogen. So I have 2, 4, 6 already drawn. So I just need the 2 more to make 8. So now if I look at my shapes, I have 3 things around it and 1 lone pair. So close your eyes to scroll. So that looks like this right here. It has 3 things around it and then 1 lone pair. So that's trigonal pyramid. Okay, and then when we look at polarity, we'll look at our electronegativities. I know hydrogen is 2.1, nitrogen is 3 something. So when you subtract, I can't remember what it is, so I'll scribble it out so I don't confuse you. But when you subtract them, you end up with something that's greater than 0.4. And we know nitrogen is the most electronegative, so we'll draw our arrows, and it gets the partial negative. Hydrogen now gets all my partial positives. Okay, and remember the shape, if we kind of go back and look at the way that the shape actually looks, this is the one that's usually a little bit more confusing. Notice how all the legs are kind of pointed down. So we have all these negatives pointed down, positives pointed down, and then we have a negative pointing up at the top. So we have a negative end and a positive N. So that means that this molecule is polar. So we know we have dipole-dipole. We know we have LDF because everything has LDF. And then we just need to look if we have hydrogen bonding. So is it H bonded to FO or N? Yes, it is. So we say we also have a hydrogen bond. The next part is just some simple terminology, just knowing the difference between ionic and covalent. The main thing is ionic always has a metal in it. So this is how you know that you're looking at an ionic substance. We know that it can dissolve in water and it conducts electricity and it has a high melting point. Our covalents are pretty much the opposite. They're just made of nonmetals. Some of them can dissolve, but not all of them. They have a low melting point and they do not conduct electricity. So if you can remember one of them, you can just remember the other one is the opposite. The last thing is just naming compounds. So the main thing to know is if you have a covalent, we always use the prefix, and then if we have an ionic, we don't. So let's look at some examples. So this is ionic only. So the only thing we're going to do is just name it. Just say the elements. So the first one is calcium. And then I have chlorine, but we know we always change the ending to ides. Okay. I do need to look at calcium and make sure it only has one option for a charge. And it does. It's only 2+, so I don't need any Roman numerals. For number 2, Cu is copper chloride. But copper has multiple charge options because it's a transition metal, so I need to choose one. I know that it's going to be +2 because if I uncrisscrossed, that's where the 2 came from, so I just put 2 in Roman numerals. For number 3, Mn is manganese, F is fluoride, and then manganese is a transition metal. It has multiple charges, so we can uncrisscross, and I know the charge is 4. Okay, so now we're just writing the formula. So Li, it has a 1+ charge. Sulfide is sulfur. It has a 2- charge. So when we crisscross, we end up with Li2S. For barium, it's a 2+ charge. Phosphate, remember if it's an 8, we know to look on the polyatomic. It's a PO4 3-. So when we crisscross, we get Ba3 and PO4 2. So remember, you can't get rid of this 4. That's part of the phosphate. So that's not going to crisscross. That stays there with the phosphate. Because if you lose it, then you just have PO, and that's not the same thing. All right, last one. We have iron, and then remember this Roman numeral is telling us a charge. So we just write a 2+. And then I know oxygen is a 2-. Here we have the same numbers, 2+, 2-, so we know those cancel out. So we just have Fe and O. All right, for covalent, I'll just go through these pretty quickly because these are much simpler. Here we have sulfur, and then remember, we have to use prefixes. So this is, my pen kind of got a little crazy there, sulfur trioxide. Here I have 2 nitrogens, so I have to write dinitrogen. The reason I didn't use a prefix for sulfur is because it was the first one and we never used mono at the beginning. This is disulfur trifluoride. Sulfur, I know there's just one because there's no prefix and it's at the beginning. And then the tri is telling me that I have 3 phosphides, phosphoruses. And then I have 2 nitrogens. Tetra is 4 fluorines, and then 1 carbon, 1 oxygen. And I believe that is it for this part of Unit 2. If you have any